These are undergraduates, and it's the second time we've done this in the context of humanitarian international projects. So this group are walking on water. You know, they're all refined sophistications of the English language and a little bit of Spanish and French. So, Madame, lead these guys on. Gracias.
Okay, good morning everyone. Thanks for coming. My name is Felipe. This is Peter, Anne, and John. We are here today to present you our project that we have been working on during our semester in our project development class. Alright, so let's get started. The treadle pumps have the potential to impact thousands of lives in a global scale. So to start our presentation, we are going to illustrate that with a video showing how treadle pumps changed people's life in India.
Many families in West Bengal, India depend on agriculture for their livelihood. Outside the monsoon season, irrigation is vital. Without it, farmers cannot grow crops to earn an income all year round. The problem isn't finding water. There's plenty of it just 2 meters underground. It's lifting it up and carrying it to the crops that's hard. For farmers like Raj Baguli, walking back and forth for 4 hours a day in temperatures reaching 45 degrees is just an exhausting fact of life.
It's hard watering the crops like this, and it takes a long time. I used to use water from ponds, but after the rainy season I couldn't farm much because the ponds go dry.
Raj is hoping all this will soon change. He's decided to invest in a treadle pump, and today it's going to be installed. The Krishak Bandhu, or Farmer's Friend, was created by IDEI. For the transformational impact that treadle pumps have on the lives of poor farmers, IDEI won an Ashton Award in 2006. Arun Jana has had his treadle pump for 2 years. He's well aware of its benefits.
I started the pump in January 2007. Since then, I have grown many types of crop. Using the profits, I have built a new house, saved some money, and got my brother married. I also plan to expand my farming.
The rugged simplicity, durability, and low maintenance of the KB pump makes it much more appealing than its mechanized counterpart.
Diesel pump is very expensive. The diesel pump pollutes a lot, it consumes a lot of diesel. A treadle pump is used for about 1,000 hours a year, and it saves up to half a ton of carbon dioxide.
As well as its environmental benefits, the treadle pump has had a huge impact on the rural poor.
The reason they are poor is because they don't have access to irrigation. If you don't have access to water, you cannot farm. So that is the difference between a rich and a poor farmer. Modern day technologies do not work for smallholder farmers.
Since winning the Ashton Award, IDEI and its founder, Amitabh Satanki, have gone from strength to strength.
To this day, we have sold 750,000 pumps. This means that it has improved the lives of between 3.5 and 4 million people. We call it the golden egg-laying goose.
Awards and investment have followed in quick succession. $27 million from the Bill and Melinda Gates Foundation, a major carbon finance deal from Climate Care, and a $1 million investment from the Acumen Fund to help sell treadle pumps and drip irrigation systems around the world. Amitabh Sadangi has also decided to diversify into yet more low-cost solutions, such as affordable drip irrigation systems. These are ideal for farmers in the drier parts of the world and are extremely energy efficient. Nearly 1/3 have been sold. For this inspired leadership, Amitabh has been feted at the World Economic Forum, the Global Philanthropic Forum, recognized as an outstanding social entrepreneur by the Schwab Foundation, and won a Scholar Award for social entrepreneurship. It's market day and a good opportunity for Arun Jana to sell his produce.
Before, I only used to grow green potatoes, so I couldn't sell them. Now I am growing a variety of vegetables and taking them to market. Every day I take vegetables to the market, almost 7 days a week.
But it's here, at his home, that the rewards of his investment are clearest to see.
My family is doing very well. My wife and children are getting clothes and proper food. My parents are also getting good clothes and food. I don't have any problems anymore.
Raj's pump is nearly finished. He's optimistic about the future.
I'm feeling very happy. Using this pump can be very beneficial. I can get more water in a short time, so I can farm more land. That means more profit, and I'll be very happy. Well, when you have money, you feel good.
And Raj foresees more than just agricultural benefits. It might just change his life.
I've planned to get married and have a family. All by farming more land using the KB pump.
IDEI has also created an impressive marketing structure to distribute information and educate farmers on the benefits of irrigation. As well as regular promotional meetings, IDEI has come up with a unique and entertaining way to get its message across. They produce their very own Bollywood movie extravaganzas. They've even won an award at the Sundance Film Festival. Farming has never looked so good.
Alright, so that video showed that treadle pumps obviously can have a great impact on the path of somebody's life. Treadle pumps can be used on a global scale, but they're mostly found in areas in Africa and Southeast Asia. For the purpose of our project, we decided to focus our scope just on the country of India. And to put things in perspective for you, we thought we could compare things in India to something that you know, the United States. So, this is probably common sight to many of you, an industrial scale irrigation system for farming in the United States. This is probably not so common, but in India it's very common. A farmer is forced to irrigate his crops with the use of just a bucket filled with water, walking from plant to plant. It's also interesting to look at the effect of farming on the economy in both countries. In America, it's 1.2% of our GDP, whereas in India it's 17% of their GDP. In America, it employs less than 5% of our workforce, whereas in India it's over 50%. So looking at those stats, it is made obvious that improving their irrigation system and improving their agriculture could have a huge impact on their economy. So, what do farmers do if they don't have treadle pumps? They kind of covered this in the video. They can rent a diesel pump, but these methods are used during the dry seasons. India has two pretty drastically different seasons. They have a monsoon season from about May to September. The rest of the year it's relatively dry and they have a hard time growing crops. So the diesel pump they can rent for about 80 rupees an hour, which translate into $1.25, which is what they allocate to live on per day for an average Indian household. So when they use a pump, they have to use it for a short period of time and flood the field, which often is not very effective, and they end up washing away the topsoil, which makes it harder to grow crops. Also, if they wanted to use manual labor instead of the diesel pump, they can fill up huge buckets of water, fill them up in a well or a pond if there's one nearby, and then transport those to their crops and water their fields. Actually, we'd like to demonstrate this. We have a classmate who's volunteered her services. She doesn't really know what she's doing yet, but we would like for her to pick up 2 buckets of water and
Lift with your feet, make sure.
what did you say?
Lift with your feet. You didn't sign a waiver or anything, so no injuries today.
So this is 6 gallons of
You
water,
can try to walk across the classroom.
which is about 50 pounds.
Spill it.
Yeah.
That's key to it as well.
So,
right here.
Yeah, that's fine for now. So how was that? Like, you noticed that it was obviously very heavy.
Yeah.
And you took it
Yeah.
just nearly like 15 feet.
Yeah.
It was also extremely hard not to spill the water. That's very, I mean, that's exactly what we were looking for you to have out of that and to understand how heavy that was to actually do. These farmers are going 300 feet, 500 feet, thank you, 300 to 500 feet one way from the river. Uneven terrain, extremely hot conditions, this is hours on end, days on end. On top of all that, these people are typically malnourished, and so that's making it even more difficult. And so right here you have the Indian population. This is a farming family. To get an understanding of both the ergonomics of what we want to do with this pump design, you have to understand the people that you're designing it for. The Indian population, an average male stands about 5'5", weighs about 60 kilograms or 130-ish pounds. A female stands about 5 feet tall and weighs about 110 pounds. So with that weight, I mean that's probably about 50 pounds.
50 pounds.
It's 50 pounds right there. I mean that's roughly half a female's body weight in just those 2 pails of water, one trip. So what impact does a treadle pump really have on the population? This kind of builds off of the video you guys just watched, and it was actually, I have some stats here based off of the company that put that video together, IDEI, or International Development Enterprises of India. And the environmental impact they touched on a little bit when they're talking about using diesel pumps. You can have a reduction of 477 kilograms of CO2 per pump per year, based off of just one of those single pumps being used or replaced by a human-powered treadle pump. Another thing to look at is the preservation of their topsoil and their farms. As you saw, the diesel pump has a very high flow rate. What that's doing is that's blowing away the topsoil on the top level. Using a treadle pump has a much slower flow rate, more controlled, more what you need when you need it. And so what that does is that preserves the fertilizer, further saving a farmer money over time. The socioeconomic impact of this was a study by the Energy Resources Institute, or TERI. They found that there was an increase of cultivated acreage of 255% around the villages that started to use treadle pumps. That's huge. That's showing that they are going from 1 crop a year nearly to 3. So I mean that's a huge impact for their area. Also, a report by the Acumen Fund on the impact of treadle pumps showed that 100% of households in the Uttar Pradesh area changed their diets to include more greens. That's more of the micronutrients, that's more strength, that's more growth. That's huge for their families as well. They're also able to find that from the profits associated with having a treadle pump and no longer spending your money with a diesel pump, that 83% of households were then able to add milk to their diet. Once again, more micronutrients, helping their bone densities, everything, as well as having livestock. That's a huge meat source as well, and definitely excellent for their family. And finally, they had 50% of the households in this area were able to then use their extra income towards schooling and learning materials for their children. This is actually a picture of Indian children in the 2nd grade pointing to their country or the country of India on a globe. So that was pretty cool, showing that the actual impact in the future of India to continue improving it over time. Yet another interesting thing from this is that in that report they're saying that typically fathers are away from their families for 7 months because they are working day in, day out, trying to keep their crops irrigated. With this treadle pump and the efficiency associated with it, they are then able to still be with their family as they only have to irrigate for maybe an hour a day compared to an entire day process.
Alright, so let's actually look at the treadle pump design. When we started looking at the treadle pump, we found it was composed of about 7 different main components. The first being the driving system. It's usually made up of a rocker arm or a pulley system, and this is what's actually used to drive the piston cylinder arrangement. It has treadles, which is what the user is going to step on, kind of like a Stairmaster to operate it. An intake and outtake for the water source, and then We have valve box here, some sort of valving system, doesn't have to be a box, but some sort of system is preventing the backflow of water so the pump can work efficiently. Inside the piston cylinder, you have your piston shaft, which connects to your drive system, and your piston seal, which actually creates the suction within the cylinder. So basically, treadle pumps, like I said, they work very similar to a Stairmaster. They use the repetitive motion up and down to create a suction between the seal and the cylinder wall. This pressure difference allows you to pull water from the ground up to 7 meters. And as we said, a valve system's typically used in treadle pumps. The valve system prevents the backflow of water so you don't have redundant work, so you're not pulling all that water up just to push it back down with the next treadle.
Okay, so an important part of our project was our benchmarking study. The objective of our benchmarking is to find and implement some good ideas that we can use to improve our prototype performance. So here we have some pictures of the different types of treadle pumps we looked at to our benchmarking. The first one is called the Super Moneymaker. It's produced by a company called Kickstart. The two next ones are different designs of treadle pumps. This one actually uses a pulley to the drive systems. And these two, they are suction pumps. They are different from the other ones that are pressure pumps. They just use the suction to get water from the ground. They are both produced by a company called Kibi. This one is actually that one that you saw in the video. It's people can actually buy the pump itself and build the frame with any available material like bamboo or something like that. And this one is just another example of a different design of treadle pump without the handlebar. So with that benchmarking data, we have this table here showing the main specifications of a treadle pump and the average values in the market. So you can see that a treadle pump has a average price of $75, and the flow rate, they have average flow rate of 4,500 liters per hour, what is about 20 gallons a minute. They have an average weight of 20 kilograms, that is about 44 pounds, and irrigation capacity of 2 acres. This data was important for us because then you can compare our results with what they have in the market today.
So now I'd like to introduce you to our actual project. For this project, we partners with the Appropriate Technology Collaborative. They're a non-government organization, and their goal is to produce sustainable technology that will give people in developing countries, the chance for socioeconomic growth. They actually already had a pre-existing ATC design that was produced by a student group a couple years ago, and their main request for this was for us to bring this closer to the market standard that Felipe talked about earlier. Some main components that they wanted us to see improve is the durability. The durability is really important for a treadle pump, especially we learned that maintenance in a lot of developing countries is not done. So if a pump breaks, most likely it'll be discarded and is no longer useful. Also, if a pump breaks, they can't afford to replace it. It's a pretty big investment for them living on $1 a day. Durability can be affected by replacing the PVC and also by looking into these initial rocket arms. Those aren't very strong. They then asked us to look at the ergonomics of their pump design. As you can see in this picture, and then also in this physical model that we have, the height that the operator would have to be is about 3 feet off the ground, which is not very safe and it's kind of awkward for them to operate. Also, the connection to the pivot system isn't quite tight enough to make those treadles purely go up and down. There's some side-to-side movement, which also interferes with their operation of the pump. They also asked about us to improve the portability. As you can see, the current frame is made out of steel, and it's one big size that you can't break down. It's set to this size, and you couldn't imagine putting that on somebody's back and carrying that to a different field or bringing it from a main city into the field that you want to use it. And lastly, they wanted our pump to be buildable in developing countries. So, using what they gave us, we built a list of key design specifications. As you can see, these encompass the ideas that they had wanted us to address. Size and weight obviously will affect the portability. things such as energy consumption, aesthetics, mechanical loading, those are all factors that relate to the usage of the consumer. And then function and performance and quality also relate back to the durability.
Alright, so we decided it'd be also useful to actually construct this model that was already previously existing. As you can see, it's up here in the front of the room. You'll have a chance later to come up and take a good look at it. But we have some interesting video, actually, of this is myself working the pump. So, as you can see, I'm pretty high in the air, about 3 feet, like Ann said. And I can operate it pretty smoothly. It draws some water, but it's not drawing a whole lot of water. That's partially due to the valve system that was used. It's kind of hunched over the handle at the top. It's not the most comfortable thing to use. It gets water pumping, but again, it could be improved on. So we have another video here. This one's a little bit more interesting. This is Ann trying to pump the pump, and as you can see, it's very difficult for Ann to get it moving. Ann's a lot more realistic to what the demographic, what the population is going to look like in India as far as size. So if it's this hard for Ann to use it, it's going to be unrealistic and hard for people elsewhere to use it as well. So here's some analysis of the original design we took. It moved about 4 gallons per minute, and that was not pumping any water upward or pulling any water. That was just at ground level, cycling water at about 4 gallons per minute. It took about 140 pounds to get the treadle operating from its static position. Once you had it moving, it was more like 45 pounds. So that initial 140 pounds to get it moving, a lot of people in India don't even have that much weight to get it moving. Obviously it's very heavy, and it was extremely costly to build.
So kind of building off what both Ann and John talked about, we really wanted to concentrate on DFM after constructing this model. And that was the fact that in the booklet that we used to construct this, there was a couple steps that were just missing. We were able to figure those out and then go from there. Specifically, that had to do with fasteners. We wanted to reduce the number of fasteners that were in the design to make it as minimal as possible, as well as the ergonomics that they both touched on. You're very high while operating this. That leads into safety concerns as well as just how comfortable you are while using the product. As a consumer, you want to feel comfortable using your product that you're going to be using for hours on hours on hours. As well as the durability. We found that PVC was not the strongest material, had a lot of flex to it. We felt that it wouldn't really last too long out in the field in the elements. And then also John talked about the cost. That was obviously American prices going to your local Home Depot. It's going to be much greater prices than you would see in foreign countries, as long as you're able to actually still buy the necessary materials that you need.
So with the experience we got by building the original design, we went to our design phase. Our project scope began defining 2 different topics. The first one is to create a pump to be manufactured in the main cities of developing countries like India or Guatemala, for example. And after our meetings with ATC and during the course of our project, we find that the areas we wanted to improve were the cylinders, pistons, piston seals, and the valving. You can see the pictures over here. The first picture, you can see the pump housing with the 2 cylinders and what we call the water chamber. In the second picture, you can see the pistons and the piston seals made of leather. And in the last picture, you can see the valve system in the bottom of the cylinder is basically a piece of rubber that allows the water to flow just in one direction.
So we'd like to just take some time to walk you through our thought process when we were designing each of these components. We'll go ahead and start with the seals. So seals looked at several different materials and types. As we mentioned, the ATC model used leather. Do you want to pass around that piece of leather for us real quick? That is the material that we used to build their seals. You can tell it's pretty rigid, it's pretty thick. It's hard for us to acquire, and because of that, we also would think that it would be hard for people in developing countries to acquire. Some downsides to leather are its durability and also just the actual attainment of it. The leather does have positives, such as it has a low coefficient of friction, and it swells when you add water to it. So it is often used as a seal material in a lot of pumps. We also looked at tire tube rubber. We found out that tires are pretty readily available, or just incredibly available in a lot of developing countries. And so we wanted to consider the usage of that rubber in our seal. Finally looked into hard rubber. Hard rubber would be nice because it would be solid. We think that it would really help with the durability of the seals. The only drawback to hard rubber is that it would have a higher coefficient of friction than the leather would. Types of seals that we looked at U-seals, piston rings, labyrinth seals, and cup seals. And cup seals are what ATC used in the original model. Benefits of labyrinth seals and U-seals are that they're completely independent of friction to seal the pump. They depend more on the flow and pressure drops. And these two typically depend on friction. We made a modification to the cup seal for our final design. We decided to use hard rubber, and we made a 1 millimeter tolerance from that seal to the cylinder so that it wouldn't rub with the sides of the cylinders and it would flow freely. Because of this, we knew that we had to create a seal around that outside edge, and so we had a small hole within that actual piston body that would allow some water to flow up, and then that would in itself seal the seal. So this is the basic two-seal configuration, which resembles what ATC had, except we just stepped it up to using metal and rubber. The rubber would be injection molded polyurethane, and we do know that injection molding is pretty available in main hubs of developing countries. So moving on to the pistons, really big consideration when we were designing pistons was design for manufacturing. As you can see, these are the parts we used for the actual piston. This is all the same bar stock, just cut to different lengths. This piece, the shortest piece, was put on the underside as a spacer. This is a piece that is meant to secure the seal in place, but still allow for the easy removal of the seals in case you need to replace them. The one consideration that we really had to focus on for the pistons is the actual calculation of the leakage path that would still allow us to attain the market standard of 7 meters of pump head. So with a simple leakage path analysis, we came up with a hole diameter of 3.5 millimeters.
All right, so the next topic that we considered improving was valves. So a few different valves that we looked at, ball check valves, we looked at gate valves, we looked at shuttle valves. Some of the more interesting ones, shuttle valves actually were brought to our attention by somebody that we consulted for information. He thought they could be used in shuttle pumps. For our design, we were looking for something that was functionable and easy to use and reliable, so we stayed away from that. Other options, the flapper valves, kind of ones pictured top right. Like we said, that was one that was currently used, and it had some problems with not sealing well. Basically, the pressure that was generated by the pump was allowing water to seep past that valve. So that's why you can get a good, consistent pump of water in those videos that we watched earlier. Ultimately, what we ended up going with is the spring-loaded check valve box, and that has many uses. The spring-loaded check valve box, like I said, it was selected for functionality and durability. It's easy to manufacture and it's low cost. Basically, and it's going to pass around. We took the idea from a check valve, a brass check valve you'd see in a standard plumbing configuration. Basically uses a spring and a nut with a bolt and a washer on top. And what that does, you have 2 ins and 2 out valves, one for each cylinder, and it allows the water to not backflow when you're trying to pump. And that there is actually a sample of a valve box. Be careful passing it around, it does have some sharp edges on it, so that was a prototype that we built, but it's basically the inside of what our valve box looks like. Here's a computer drawing up on the screen, that's a hard version of it, but we had some calculations in the spring that we would need. Obviously, we couldn't just put any spring in there. It needed to be durable, and it also needed to be able to open. We didn't want to put too strong a spring in there. Our valves wouldn't open. We'd have a problem. We wouldn't pump any water. 2 was the spring that wouldn't hold the seal. So a little bit of delicate calculation there as far as picking just the right springs. Also with the valve box, we were able to incorporate a filter into the valve box, and basically what that does is it prolongs the life of your seals. It keeps rocks and grit and sand and stuff out of the pump, which again, it increases our service life. Maintenance isn't really done as we've already said, so any increase in the life of the product is good. The cylinders, these are finished product cylinders, sitting on top of the valve box actually. It's interesting we added to the cylinders is that path on the top of the cylinders. It allows water to travel back and forth from cylinder to cylinder, so when the piston comes to the top of one cylinder, the water flows over to the other one and fills it. That helps with a couple things. It helps with keeping the seal around the piston while the pump is moving, and it also helps keep it easy to move in there. It doesn't bind up because of friction as much. So, interesting little adaptation that we saw on some other treadle pumps in industry, so we decided to use that in ours. Also, a lot of the pumps used a large intake that was, you had to put a large piece of reinforced hose over in order to get the water to. Our valve box, as you can see on there, we used just standard 5/8 garden hose. It was easier to use and more readily available than a large 1.5" or larger diameter hose.
Okay, and so even though it was out of our actual project's main focus, we still felt it was appropriate to come up with a treadle frame as well as a treadle concept. So what you have here in the top left is our actual treadle frame as well as right in front of you. We tried to use as much, we used wood, we felt that that was readily available as well as replaceable. In the earlier video you saw that that could also be constructed out of something like bamboo. Going from there, you can then see our treadles. We wanted to look into ergonomics with this design, which is why we ended up putting about a 6-inch drop in the treadles. That was to help combat some of the issues we saw with how high the user was on this model. As well as you can also see that the aesthetics of the unit, we wanted to base it off of the Indian flag. We felt that that would help with the diffusion of this product, and that it would make people want to use it, want that model. In the top right, you can see our calculation for mechanical advantage, and that is what is the actual force you can gain by using a levered device. With our model, which is option number 2, and that is taking the length of the overall treadle and where the user would put their force down, divided by the actual distance from the fulcrum to where the piston force is. And we had about a mechanical advantage of 3.25. That's 26 inches divided by 8 inches there. And so that allows the operator to get 3.25 times their weight of force on that piston, giving them pump a larger head as well as moving water a further distance.
Right, so here you can see some pictures of our pump construction. On this side you can see the pictures of the pump housing and the valve box. You can see in the first picture the in and out valves. In the second picture you can see the check valves mechanism. And the last picture is the pump housing basically done with the cylinders welded in the top of it. In the center you can see the work we did with the pistons. In the first picture you can see the sheet metal you use it to the piston and the piston plate. In the second picture, as Ann said, you can see the Z. It's welded to the piston plate. It holds the seal in the piston, and it helps the user to eventually change the seal. And this picture is our piston. It's our final piston. And finally, here you can see our treadle frame. It's, as Peter said, basically made of wood. In the second picture, we already have the treadles attached and the rocker arm. And the last picture is our pumps basically done with the frame, treadles, rocker arm, and the pump housing. Can you go back a little bit? Alright, so during the whole process, we wanted to document it as much as we can, because we are going to build our structural manual after that. So we took pictures of all the steps, and we want our manual to be as explanatory as possible. We also tried to use the tools and process that would be available in a developing country. So we basically used hand tools and welding. So here's a picture of our final prototype, and after testing it, we could compare with the original design. So here we have our new design with water flow rate of 10 gallons a minute compared to 4 gallons a minute. That's 250% of improvement. We got 450% of improvement in the operation force and 183% of improvement in the weight. We spent around $400 to build the original design, and we spent like about $100 to build our new design. That's about 406% of improvement in cost.
So that detailed our process from beginning to end of how we achieved the pump that we ended up with. I would like to take a quick moment to extend a thank you to everybody that helped us on our way. First, we have ATC. They were excellent in their consulting. We had several meetings with them throughout the semester where they gave us guidance and helped us figure out what would be the best approach for us to take this project. We'd also like to thank the guys in the machine shop in the engineering building. They put so much time into this, helping us figure out how we were going to build each prototype. It was amazing. And lastly, I want to thank all of our consultants, including Dr. Thompson, for helping enrich our understanding of treadle pumps. And then before we conclude, or I guess we would like to conclude with a video that we took while testing our pump to see if it could achieve the suction head of 7 meters, which we were successful in doing, which for us was absolutely amazing. We're beyond thrilled that it's able to do that, and it's brought so much closer to the market standard.
Visions of employment in Hollywood or Bollywood. The wows just fill us with awe as mere professors to think that you've accomplished so much in such a short time. So on behalf of the old geezers and a couple of old ladies in the group, thank you so much. But questions from the floor?
Can you give me an idea of that $100 cost at the end? How much of it is accounted for by what parts?
Oh.
Just give me an idea.
I would say the majority of the cost was in the sheet metal for the valve box and the cylinders.
You mean that orange piece there?
Exactly, the orange piece, which the orange piece is kind of symbolic of our project scope. That was really the main focus of the project. And so that's where the majority of the cost was spent in metal supplies. Obviously, 2x4s and 4x4s of wood there, they weren't the majority of that cost. I would say probably 60% of that cost was the actual metal that goes into it. Metal tubing and the bar stock and the sheet metal.
We've also done a separated cost analysis of that orange piece alone. That's what we would envision the manual accompanying, and that's what would then be produced in the developing countries and the main cities. And do you remember what cost we had for that?
It was around just over $50, I believe, for the actual, for that portion of it. So I'd say about 60% of the cost went into that part.
Mm-hmm. And in, supposedly or hypothetically, in a developing country, a farmer could use bamboo for the remainder of that pump and save themselves half the cost.
Or whatever materials.
Bamboo, yeah, whatever materials they have available.
Is ATC going to use your improvements and/or pump design?
We certainly
that's a
hope
big
so.
question.
We'd like to hope so, right?
They're sitting front and center here, so.
The original treadle pump, the large machine there, has been used by, well, it's been downloaded over 3,700 times. And it's been used as the basis of a design for a treadle pump thousands of times. And this other one is so much better. So it will replace the set of drawings that are represented by that first pump with the set of drawings that represent the second pump. And we expect to get greater traction with it. So yeah, it'll get used.
Yeah.
Is there any advantage to also consider using a rotary motion to convert to linear motion like this? Because bicycles are used a lot.
Yep.
In that part of the world.
Yeah,
is
we-
there any
we-
advantage to that?
I'm gonna take that one.
Yeah, we actually had that concept as well. If we had more time, if we had another semester, we really were excited by the idea of actually making the entire frame out of a bicycle. And then literally just cutting it down and re-welding it, and every component would be then turned into this frame. And so bicycles are everywhere, especially in India. I mean, that's a main mode of transportation. So, absolutely, that rotary idea was thought of.
Did you do any force analysis, if it brings a requirement down, body posture issues for repetitive motion? A lot of those families, their kids are all part of the whole operation.
Right, yeah, and we saw that as well.
So those kinds of, is there advantages from that perspective?
I imagine there would be with the rotary motion. Once again, once we had to finally put our focus into the actual cylinder as well as piston, we kind of started to get away from that. But absolutely, I imagine that there would be.
Next group.
Yeah, of course, yep, the continuation of this project.
Considering fatigue and ergonomics, how long would you recommend an Indian farmer continuously tread on your device?
I don't think in one setting there would be any issue with, I mean, there's no friction in the pump. I can get on, there's no water in it, but there is no real rubbing on the pump. It goes up and down really easily. So I wouldn't say that in one setting there would be a time limit. But we did design this with the intention that it would last 3 to 5 years without.
For service life.
Yeah, for the service life.
But I mean, you could tread a lot. I mean, I know in the making of that video, we had Ann treadling for an hour and a half, taking different clips of the video, and
No, it wasn't.
like she was tired or anything. So
It slides very easily. There's no difficulty whatsoever. It's night and day, I would say.
The IDEI video said that they went from carrying water
Yeah.
all day long and into the night to an hour's worth of pumping was enough for a farmer to get the water on their field, so.
Right.
I think you'd avoid repetitive stress injuries with the efficiency of it.
How did you choose the cylinder diameter? What was that based upon?
That was based upon the availability of seals that we had. We chose a seal that we liked, and then designed our piston cylinders around that seal. So that's how the diameter was chosen, and our stroke height was chosen based on a comfortable ergonomic feel, I guess, is what we went with, based on the height of the people in India being a little bit smaller, so it's why the stroke height's a little bit less in the pump on the right than it is in the left.
As well as the smaller cylinder you use, the more pump head you have. In India, we found that the average water table is only 2 meters down. It's only 6 feet. So you don't really need a very narrow, long cylinder for that pump head. Relatively flat terrain. It wasn't necessary. We felt that that was the best way to keep it as low to the ground and comfortable to use still.
Yes.
Did you consider adding some kind of a balance bar like the older model has? to make it-
Yes, we absolutely did. And we felt that the material is readily available that could absolutely be added to it without any more concern. We saw a video of a Stanford pump, and we decided that we could compete with that one as well. And they did not use a balance bar, and so we felt that we didn't need to either. And we felt that it was really important to show that Ann could use this without a balance bar. It's very easy to use. You don't need it. I think that in our final manual, it'll say, yes, have a 3-foot bar by 1.5 bar for stability
The
for
option.
extended periods of time. Yeah.
Something where it's added cost, so if they want to add it for their own benefit, they can, but the product that's there it doesn't need it really.
And it doesn't really have to hold that much force, it would more just be a balancing part compared to, so it could be a simple piece of bamboo or anything like that.
Any other questions? Yeah?
It's impressive to have an administrator come to a meeting like this and ask questions. I mean, I'm almost impressed.
I'm gonna put one on the head.
By all means.
My question is not related to a design, but the locals there, they do the digging to get to the water table, or they need special equipment?
There's a variety of, oh, do you wanna add? Well, in some cases, the treadle pump, yes, you need to dig down to reach the water table. In other situations, there would be a riverbed right next, nearby that you would place a hose into. I believe they do need a special method to dig down.
They have drills,
Yeah.
manually operated drills where you just drill and then you lift it out and then you drill a little bit further and you lift it out, and at the end of the day you've got yourself a well that's 6, 12 feet deep.
So that's routine for them to access the water.
Yep.
What's nice is they do have a pretty low water table. I mean, some places here you have to go 150, 200 feet to get a good stream of water. In India, like the video said, it's only about 2 meters down, so that was one advantage we had.
This isn't for everywhere because there are a lot of places where the water table is much lower. You can't pull water up more than, I mean, you guys got 7 meters?
We got 7.
That's pretty much the theoretical maximum you can pull water. Yeah.
Well, John, this is MSU, dude. We can't play basketball, but we can do engineering, not like schools down the street. Time for a final brief question.
How much more time in terms of labor did you have versus like the old model and the new model?
We actually put more into the first, well, we put more thinking time into this, but this,
More construction.
we definitely took longer to construct the first model.
Because we've got a lot of experience building this one, so.
I think experience, and then we were following the manual step by step, and I think it's harder when you're following somebody else's instructions rather than your own. And I think Felipe even mentioned that bringing, for the manual for this pump, we want it to be incredibly clear so that like an elementary student would be able to understand.
Well, lady and gents, or lady with the pink shoes and gents, we appreciate your help in terms of setting the standard for Friday's presentation and Monday's presentation, because the bar is just super, super, super high. So on the behalf, again, of the faculty, we applaud you as leaders of tomorrow to transform life on this humble planet. Thank you so much.
So that way you don't have your first otherwise they start trying I spent 2 years. He sent us this whole presentation.
His experiences in projects like this changed his whole